Namaste everyone, my name is Kunal Dahiya. I am a research scholar at IIT Delhi. I will present SiameseXML, which is a novel probabilistic framework that motivates a modular approach melding Siamese architectures with high capacity extreme classifiers. The associated paper was published in ICML this year. First, let me take a few minutes to give you a brief overview of extreme multi-label learning that deals with problems with millions of labels. The aim in extreme multi-label learning is to tag a data point with the most relevant subset of labels from an extremely large label set. Note that the problem is multi-label, where each label may be present or absent independently. When a new user or a data point comes in at test time, then we can simply apply the learned extreme classifier to return the most relevant subset of labels either as a bag or as a ranked list depending on the application. So, as you can see, extreme classification opens up a new paradigm for reformulating ranking as well as recommendation applications. In particular, each item to be ranked or recommended is treated as a separate labels in a multi-label classifier. Now, you might ask, where are you going to get problems with millions of labels? Well, let's take a look at some real-world applications. Anil likes playing the game of Go and widgets the Wikipedia page for the list of Go players. Can we recommend other Wikipedia web pages that Anil might be interested in? This problem can be reformulated as an extreme classification problem by treating each web page as a separate label. Then, on the other hand, sequence-to-sequence matching, where an input text sequence is to be matched to a relevant output text sequence, is a fundamental NLP problem, which has found applications in translation, query autosuggest, text summarization, and so on. One such concrete application critical to Bing ads is the task of matching user queries to advertiser bid phrases or keywords. Please note that the constraint of having to match billions of user queries per day to advertiser bid phrases in real time means two things. First, the keywords retrieved for a user query have to be super accurate, and second, the prediction has to be done under strict latency limits of a few milliseconds per query. Formalizing the notation, each data point has feature xi and a sparse label vector yi of length L. Further, each label L has features ZL associated with it. Note that we are primarily considering scenarios where both xi and zl are computed from the associated text. For example, xi is computed from list of Go players and ZL can be computed using Go professional or list of top title holders in Go, etc. in this particular example. The goal is to learn the parameters theta for embedding architecture and the extreme classifiers WL by optimizing the loss, that is script L. Unfortunately, doing so can be computationally prohibitive as it has order NL terms where both N and L can run into hundreds of millions. Label metadata has been demonstrated to lead to more accurate representations, especially for tail labels. Note that in real-world applications, majority of the labels are tagged with a few training points. These are typically referred as tail labels in the community. Siamese architectures, which are popularly used in such applications, focus mostly on zero-shot labels. While zero-shot labels are important, few-shot labels are equally, if not more critical in ranking and recommendation applications. SiameseXML casts the retrieval of few-shot labels as a classification task and proposes a novel framework that melds Siamese architectures with extreme classifiers. SiameseXML offers generalization bounds and achieves state-of-the-art accuracy on publicly available benchmark datasets as well as improvements on proprietary applications. We observe that the label representation learned on the basis of label text, that is EZL, can themselves be presented as data points to the one versus all classifiers WM. The paper argues that in several real-life situations, the optimal model can be expected to assign the labels to themselves with high confidence. The paper formally develops the notion of epsilon cell proximity for the same. This motivates a multi-stage training strategy where label embeddings (EZL) are initially treated as classifiers, and a Siamese task loss such as L1 is used to learn the embedding model parameters. Subsequently, the von Neumann classifiers are reparameterized as a combination of EZL and a refinement vector eta L, which are learned by optimizing a classification loss such as L2. We established that this strategy yields a provably accurate model under standard assumptions if a model ensuring epsilon cell proximity exists. Recall that we need to learn the embedding architecture E theta as well as the classifier W. Jointly learning E theta and W in a traditional von Neumann fashion can be computationally prohibitive at the extreme scale. Recall that we are dealing with 100 million labels. We resort to the DeepXML pipeline, which breaks the learning problem into 4 modules. First module, learn an embedding architecture using a Siamese style loss. This directly follows from the epsilon cell proximity notion that we discussed earlier. Note that E theta is then frozen for subsequent modules, which can significantly enhance the scalability of the overall pipeline. Second module mines order log-L hard negative labels for each data points using an approximate nearest neighbor structure that is learned only once during the training. Module 3 reparameterizes the label representation as a combination of label embedding that is based on label text and a free vector. Finally, fourth module learn the free vector eta L using the positives and only the sampled hard negative for each data point. Note that such a training pipeline cuts down the training cost to order n log L compared to order nl. This is achieved by considering order log L labels for each data points instead of all L labels. We also provide generalization bounds for module 1 as well as module 4 training. In particular, SiameseXML offers generalization bounds for its module 1 that are independent of the number of labels based on a novel Moiré type specification lemma. SiameseXML presents a general pipeline with support for various feature architectures, including BERT. In particular, this paper performed experiments on a frugal bag of embedding based architecture to meet the low latency requirements of our application. In module 1, SiameseXML uses in-batch sampling to learn label centroids alongside label text-based embeddings. It then samples order log-L hard negatives using an approximate nearest neighbor structure trained over these label representations in module 2. At prediction time, SiameseXML uses the same nearest neighbor structure to make predictions in order log-L time. We present results on multiple publicly available benchmark datasets with up to 1.3 million labels. These include diverse set of applications such as product-to-product recommendations as well as recommending similar Wikipedia web pages. We also present results for matching user queries to advertiser bid phrases with up to 100 million labels. SiameseXML can be 2 to 13% more accurate than leading methods such as Eclair, MAC, and Attention XML in both vanilla as well as propensity scored precision matrices. Note that the gains in propensity scored precision matrices reflect that the gains were more prominent on tail labels or few short labels, which are the focus of the paper. Moreover, SiameseXML can also be 2 to 68 times faster at training. This allows SiameseXML to scale to multiple real-world applications with hundreds of millions of labels. For example, SiameseXML could be trained within 2 days on a dataset for matching user queries to advertiser bid phrases with 100 million labels, where it could be 6 to 21% more accurate as compared to the baselines such as TwinBERT and Parallel. Furthermore, SiameseXML was deployed on the Bing search engine to perform A/B tests on live search engine traffic for the same application, where it led to 1.4% gain in click yield over an ensemble of leading IR, XML, generative, and graph-based techniques running in production. Finally, Siamese XML can make predictions in a few milliseconds on a single CPU core, thus making it suitable for real-time predictions. On the other hand, in qualitative analysis, we found that Siamese XML increased the quality of predictions by 11% over the baselines. To conclude, we presented the Siamese XML framework, which not only yields state-of-the-art accuracies on public benchmark datasets, but it also led to a significant gain in real-world applications. In terms of discussion points, there has been a ton of work on negative sampling, which treat negative sampling as an independent problem. However, it should be studied in conjunction with the applied architecture. The notion of hard negatives and negative sampling can change with the architecture. Finally, while our model led to significant gains in terms of multiple matrices such as precision, NDCG, click yield, revenue, etc. It would be interesting to evaluate ours as well as predictions of other models on matrices like fairness and diversity. This is important since we are dealing with models with billions of parameters. Thank you. Namaste.